Welcome back to the Special Functions and Number Theory seminar. We had a quite long summer break, but we are back with a bang. Our first talk in this semester seminar is by Professor George Andrews from Penn State University, who needs no introduction. He is one of the world's foremost authorities in theory of partitions, Q-series, number theory, combinatorics in general. And today he'll be talking on extension, McMahon's generalizations of sums of divisors. Over to you, Professor Andrews.
Thank you, Atul. Thank you, Gaurav. Thank you, everyone, for inviting me to participate in this seminar. I apologize for the fact that I had hoped to be able to share the screen from my end, but the capabilities of Zoom this morning were inadequate for that particular goal. And so the slides will be run from India, and consequently at each stage, I will be asking for the next slide, which I ask for right now. Next slide, please. So this is joint work with Tewodros Amdeverhan and Roberto Tarraso, and I'm also going to refer to some earlier work I did with Simon Rose. Next slide. Much of it's going to be about McMahon. As you can see, my tie this morning is Ramanujan. McMahon and Ramanujan were great friends, and the work this morning will tie in greatly with Ramanujan, but this is P.A. McMahon, the British combinatorialists of the 19th and early 20th century, whose work on this topic has now really sort of started to catch fire again. And so I want to give you a little background on it. Next slide, please. I should also apologize for the fact that I have a cold this morning, so that if I cough a lot, I hope that you will forgive me. McMahon's starting point is that the number of divisors of n is also the number of partitions of n into parts of only one size. So this is basically the idea we learned in elementary school, that multiplication is repeated addition. And so the divisors divide the number by just adding them to themselves a number of times. And so you see here this perfect correspondence between the divisors of 6 and the partitions of 6 into parts of exactly one size. Next slide, please. So if we let d of n denote the number of divisors of n and sigma 1 of n, the sum of the divisors of n, then these are easily seen to be the generating functions. To see this, all you need to do is to expand the summand in a geometric or binomial series in the second case, and then sum on n, and you will see explicitly that you get, in the first case, the counting the number of divisors of n, and in the second case, the sum of the divisors of n. Next slide, please. This A1 is especially interesting because A1 of Q, this generating function for the sum of the divisors of n, is one basically a linear combination related to one of the essential quasi-modular forms. Next slide, please. So I don't want to spend a long time on quasi-modular forms today, except that basically they're called that because they transform like modular forms almost. Under the transformations of the modular group, E2 will transform perfectly as modular forms do, except that there's an extra constant floating around outside. So this is the world of quasi-modular forms, but I'm not really interested in their analytic character. I just want to point out to you where they lie. They were studied extensively by Ramanujan. Of course, he did not use that term, but he has many papers related to them. And the ring of quasi-modular forms is generated by E2, E4, and E6, or equivalently by E2 and this differential operator Q, D, DQ. Next slide, please. So what McMahon does is to consider a multiple sum where he looks, instead of partitions with one part, partitions with k parts. So if k is equal to 1, we are back to the previous slides. But if k is larger than 1, then we have an analog of the number of divisors, and AKQ is an analog of the sum of the divisors. Next slide, please. McMahon conjectured that AKQ, this second series, is in the ring of quasi-modular forms, and he proved this for k equal 2, 3, and 4. And in 2013, Simon Rose and I proved that indeed these are all in the ring of quasi-modular forms. Next slide, please. The crux of the proof relies on the following identity. Suppose that Tn of x is the nth Chebyshev polynomial. So this is the classical Chebyshev polynomial. It is the polynomial that relates cosine of n theta to a polynomial in cosine of theta. So that's the definition of it. So now I'm going to define this sort of semi theta series where q to the n squared plus n is the theta component, but the coefficient of q to the n squared plus n is this 2 to t sub n, 2n plus 1 x over 2. And it turns out then that f of x and q happens to be effectively, with this infinite product out front, the generating function for the ak of q. And I basically want to go through that. So next slide, please. So, sorry. That's the terrible thing about these slides, is neither you nor I know what the next slide will be. So they're corollaries of this identity. I'm going to prove this identity, but the corollaries of it are that we get an exact form for the ak of q, and we get a recurrence relation for the ak of q, and the recurrence relation is basically adequate to show that the ak of q are indeed modular forms. Next slide, please. So how do you prove this main identity relating this f of xq, which is a sort of semi-theta series, to the generating function for the ak? So we start out with the fxq as defined on the previous page. Next slide, please. And that is the cosine of 2n plus 1 times theta. And what is 2n cosine of 2n plus 1? 2 times that cosine is e to the I plus e to the minus I times this argument. And now we can change this sum into a bilateral series by replacing in the first sum n by minus n minus 1, and it turns into the second factor. And so we have a classic theta series. Next slide, please. And that theta series is an instance of Jacobi's triple product, which we have written here at the bottom of the page. Next slide, please. And so what we have now, returning to getting things in line where we can get x involved, we can rewrite this in terms of the cosines. Next slide, please. And now remember, x is equal to 2 cosine theta. So now we know that for the identity for cosine of 2 theta in terms of cosine theta. And so we put x back in. And now, next slide, please. You can rewrite the infinite product this way. You factor out the 1 minus q to the 2n squared. And next slide, please. And you obtain this last expression, which, when we expand the product in the obvious way, it becomes equal to, next slide, the exact generating function for the ak of q squared. And so all one does is to replace q squared by q, and you're back to the proof of the original theorem. Next slide, please. So that's so Simon Rose was interested in applications in algebraic geometry, actually. And so, but what he needed was this identity that put that forced these AKQ into the world of quasi-modular forms. And so he and I both left it right there. And then recently, M. de Berhan and Tarasso and I actually, M. de Berhan is the one who noticed that there was something going on here besides just that particular application. And among other things, these coefficients have a lot of arithmetic interest. So I give a sample at the bottom of this slide of congruences for this MO, says McMahon's original function, is why it's MO, of various Ks and various various arguments n, where you have congruences mod 3, 5, and 7. I will mention a congruence related to 11 later, and there are other congruences related to 3 and 5. So what I'm giving you here is just a sample of what we have in our paper. I mentioned in the abstract, incidentally, where this appears in research and in research in the mathematical sciences, I believe it's called. Anyway, it's Ken Ono's main journal. And so the full paper appears there. I don't have it listed in the slides, but it's in the abstract. And so how do you prove any of these? So I will give you just a simple case, because I will do a case where it's easiest to actually prove these, but you will get the idea of it. So I want to show that if n is not divisible by 3, then MO of 2 and n is congruent to 0 mod 3. So here's a 2 of n, and I had on the previous slide given you a formula for the AK of n, and so here it is specialized to the case k equal 2, and now I'm going to look at this from a congruential point of view mod 3. Next slide, please. And so the fact that this infinite product out front is cubed, you can bring the 3 inside, because 1 minus x cubed is congruent. 1 minus x quantity cubed is congruent to 1 minus x cubed mod 3. And so now we have q cubed infinity, and the same series. Next slide, please. And so all we need to do is examine when this thing in the numerator can have q to a power 3n plus 1 or 3n plus 2. Well, since it's q is raised to the binomial coefficient k plus 1 choose 2, k plus 1 choose 2 is never congruent to 2 mod 3. Hence, in the numerator, there's never a power of q congruent to 2 mod 3. And so MO of 2, 3n plus 2 has to be 0 mod 3. On the other hand, next slide, please. If you wanted an exponent congruent to 1 mod 3, the only time that occurs is when k is congruent to 1 mod 3. And then there is this 2k plus 1 factor in this sum. And when k is congruent to 1 mod 3, 2k plus 1 is congruent to 0 mod 3. And so you get MO of 2 and 3n plus 1 congruent to 0 mod 3. So there are examples of proofs of these sorts of congruences. Next slide, please. So at the end of our paper, we conjectured that MO of 10 and 11n plus 7 is congruent to 0 mod 11, and this was subsequently proved also by my co-author M. de Berhan, but now Ken Ono and Anjit Singh. Next slide, please. So all of this is somehow prelude, because all of this relates to things that have been in the literature for, I would say, at least a year. But now the next results I'm going to talk about are not published. So suppose instead of looking at the series that we had before, we look at a series that looks very much like it, except instead of in the denominator, the factors are all of the form 1 plus a q to the n plus q to the 2n. Now, if a is minus 2, then the denominator is 1 minus q to the n quantity squared, and we're back to all the previous work. Next slide, please. However, all the cases where 1 plus ax plus x squared equals 0 has roots of unity as roots, these are of interest because these will put us in the world of the quasi-modular forms. And so how many a's are there? There are not that many. There are 5 of them that will have this quadratic equation have roots that are roots of unity. A equals 0, plus or minus 1, and plus or minus 2. Next slide, please. So let's start with a equal 1 and t equal 2. So here is this u2 of 1 and q. A is 1, t is 2, q to the n1 plus n2, and then these two denominator factors, 1 plus q to the n1 plus q to the 2n1, and the same thing for n2. And let's get out our favorite computer algebra package and expand this in a power series. Well, obviously, since n1 is greater than or equal to 1 and n2 is greater than n1, the first possible value you can have is q to the n1 plus n2, where the first one is 1 and the second one is 2. So the series has got to start out at q cubed. Next slide, please. Surprisingly, there is no q to the 4th and q to the 5th. The next thing to appear is q to the 6th with a coefficient of 3. Next slide, please. There's no q to the 7th and q to the 8th, and there's 4q to the 9th. Next slide, please. And this runs on so that one starts to think there might be something going on here. So obviously, as everyone watching would do, you take the series 1, 3, 4, 7, 6, 12, 8, which seemed to me when I first saw it quite random, and you run off to the OEIS. Next slide, please. And up comes a 000203. It's the sum of the divisors of n. So what we have, next slide, please, is a conjecture that this double series is equal to this series in q cubed. There's, as you look at the left-hand side, there's no hint at all that this is a function of q cubed, but it turns out to be so. And so, furthermore, this again makes clear, at least in this case, that we are in the world of quasi-modular forms, because this is the original quasi-modular form A2 with q replaced by q cubed. Next slide, please. So the answer is yes, this is true, and we will provide a combinatorial proof. Okay. Next slide, please. First, before we provide a combinatorial proof, we show that the crucial identity to establish the quasi-modular form nature of the UT of AQ for these 5 cases. Next slide, please. So I'm going to change the previous assertion about that Simon Rose and I proved, because the Chebyshev polynomials are alternatively even functions and odd functions. So the t's with an even index are polynomials that are even functions of x, and those with an odd subscript are odd functions of x. So what I'm going to do is to take the Chebyshev odds of n of x to be the odd t 2n plus 1, and I'm going to get rid of the fact that it is an odd function of x by replacing x by the square root of x, dividing by the square root of x. So now I just have an ordinary polynomial in x. And so the result that I asserted, that Simon Rose and I proved, can now be restated exactly like this without the necessity of carrying along q squared, etc. So next slide, please. So consequently, these ut of a, q, and x, their generating function is this infinite product, just as Simon Rose and I saw in the original case. Next slide, please. And so what one does is the same thing that you did before with factoring out the denominator. And let me point out that the main thing going on, the reason you want the 1 plus ax plus x squared equals 0 to have roots of unity is because you want this infinite product out front to actually be one of the classical theta functions, which it will be if a is if the roots of that polynomial are roots of unity. Next slide, please. And so now you are going to fix things up so that it looks like the previous case that we were working on. Namely, you have now x plus a plus 2 as you put 1 minus q to the n squared in the denominator. And next slide, please. And so finally, what you wind up with is that this infinite product now relates back to our original formula with Simon Rose, except the argument of the new odd Chebyshev polynomial is now x plus a plus 2 over 4. And so we now have the expression that we wanted for this generating function for the ut of a and q. Next slide, please. So I'm now going to turn to proving this this identity combinatorially. So as it stands, there isn't, what we need to do is to massage the infinite series so that it somehow looks more like a problem in partitions. Next slide, please. So how do we do that? Well, the 1 plus q x plus x squared is equal to 1 minus x cubed over 1 minus x. And so we apply that algebraic observation to the series at the top of the screen. And what we obtain is this second line where we now have the nice binary factors that arise in all q series. And in the third line, I distribute the q to the n1 plus n2 over these two factors in the numerator. And now I'm going to assert that there are that what is being generated there is a difference between two partition functions. And I'm going to explain why it is such a difference. Next slide, please. So you expand the denominator in that series. And so the series that we see that we have involved is actually a product of these two things where I've expanded the denominator in a geometric series. So let me go through carefully what's happening here. In the first factor you see in the top, you have q to the n1, and its coefficient, the number of times it appears as a part, is either congruent to 1 mod 3 or 2 mod 3, and you get a plus contribution if it's 1 mod 3 and a minus if it's 2 mod 3. And similarly for the second factor. So what does this mean when you multiply the two together? It means that you're looking at a partition into two parts where the frequency of each part is never a multiple of 3. It's either congruent to 1 mod 3 or congruent to 2 mod 3. And when do you get a plus sign? You get a plus sign when either you're using both frequencies congruent to 1 mod 3 or frequencies congruent to 2 mod 3, and you get a minus sign when the frequencies are not congruent mod 3. Next slide, please. So following up on that, you get plus for P0 of n. It's the number of partitions of n into two different parts. I emphasize they are different is different. One uses difference instead of distinct to mean there are two parts that are numerically different, but each may be repeated many times. N1 appears F1 times, N2 appears F2 times. And remember what I said on the previous slide, the frequencies are never divisible by 3. So 3 does not divide F1, 3 does not divide F2. And to get a plus sign, F1 must be congruent to F2 mod 3. Next slide, please. Well, this is exactly the same slide, except now we're dealing with P1. It's the same idea. You have two parts, each may be repeated. The N1 appears F1 times, N2 appears F2 times. The only difference between this and the previous slide is that F1 is not congruent to F2 mod 3. And so this series that we have is a generating function for the difference between P0 of n and P1 of n. Next slide, please. So here's what we want to prove. We want to prove that the difference between these things is identically 0 if 3 doesn't divide n, and it's the sum of the divisors of n over 3 if 3 divides n. So in the following, I'm going to use this partition theoretic notation, which is confusing to outsiders. I don't know how many people unfamiliar with partitions are here today, but in any event, we write n to the f1 and n2 to the f2 with exponents, meaning the partition where n1 is repeated f1 times and n2 is repeated f2 times. Okay. All right. And so here is the injection that I'm going to move P1 partitions into P2 not P. P2 should be P0. Sorry about that. But the partitions where the frequencies are not congruent into partitions where the frequencies are congruent. And so the mapping is this. I change N1 appearing F1 times, N2 appearing F2 times to N1 plus N2 appearing F1 times, and N2 appearing F2 minus F1 times. So it doesn't matter. Without a loss of generality, we will assume that F2 is greater than F1, so that I don't have to go through two cases here. But they are the same case, perfect symmetry. And so, look, am I telling the truth? So F1 is congruent to F2. Neither is congruent to 0 mod 3. They're either 1 or 2 mod 3. And now F2 minus F1 is not congruent to F2, because if it were congruent to F2, this would, anyway, you can easily work it out that F2 minus F1 is not congruent to F1. And so I have mapped partitions from P1 into partitions P0. Next slide, please. And here's the inverse mapping backwards. And you map backwards just by the idea that now you take the largest part and subtract N1 from N2. Remember, these are different parts. So one part is bigger than the other one. And so you make this map back, and if F1 and F2 are not congruent, then the exponents F1 and F1 plus F2 are congruent. So I have moved back into P0. Next slide, please. Whoops. It appears we produced a bijection in every single case, which would imply P0 of n equals P1 of n. Always. And this indeed contradicts the first instance that we have, where P0 of 3 is 1 and P1 of 3 is 0. So most of you familiar with the theory of partitions remember Fabian Franklin's proof of Euler's pentagonal number theorem, where at first glance it appears he's proved that Euler's pentagonal number product is actually identically equal to 1. But it turns out there are a few rogue partitions that don't work in his bijection, and that's where you get the pentagonal number series. And the same is true here. Next slide, please. When and how can this bijection fail? Because obviously it does fail sometimes. Next slide, please. The only case of failure is when N2 is equal to D and N1 is equal to 2D, because the inverse map is a fine map, except it maps it all. The now parts are identical, because remember, the new part created is N1 minus N2, and that 2D minus D is D. And so you have ruined the bijection, because the map maps this partition outside the partitions in P0. So when does this failure occur? Next slide, please. So let's examine this case where we are in P0, because we have partitions like this and they have no pre-image in P1. So F1 is congruent to F2 mod 3. So in this case, N is F1 times 2D plus F2 times D, which is D times 2F1 plus F2. And F1 is congruent to F2, so this is 3. And so N is congruent to 0 mod 3. So the only numbers that can be partitioned where this bijection doesn't work are numbers where N is divisible by 3. So if 3 doesn't divide N, the bijection always works. And we know we have the top line of our assertion in the theorem, which is that P0 of N minus P1 of N is 0 if 3 does not divide N. However, that's great, but what happens if 3 does divide N? Next slide, please. So what about the case N equals 3 times nu? How many ways can we solve F1 times 2D plus F2 times D equals 3 nu? Well, D is a divisor of nu. And so, so we have 2F1 plus F2 equals 3 nu divided by D. And this is uniquely solvable for F1, provided 3 times nu over D minus F2 is even, because all we need to do is divide that even number by 2 to get F1. Next slide, please. So putting in F1, we can easily, we have either 1 or 2, but not both, will be an answer. Either 4 and 5, but not both, will be an answer. Either 7 or 8, but not both, will be an answer, etc. You can, you have these choices to make all the way up to 3 nu over D minus 1. And how many of these choices are there? There are nu over D choices for F2. And so consequently, next slide, please. For each divisor D of nu, remember N equals 3 nu, and there are nu over D P0 partitions that have no pre-image in P1. Next slide, please. Hence, P0 of 3 nu minus P1 of 3 nu is the summation over D divides nu of nu over D, which is the summation of D divides nu of D, which is sigma 1 of nu, which is sigma 1 of N over 3, and that proves the original theorem. I should remark that in the paper that we are writing, there's also an analytic proof. Indeed, the first proof we proved of this was an analytic proof, but the thing that I wanted to bring to the fore in this is there are interesting combinatorial aspects of this generalization of McMahon's idea, and this is indeed one of the prettiest of the things that arises here. Next slide, please. So here's an example. I want to show you how the operation works. You start out, as we did in the proof, with we're taking the partitions of N equals 7, where the frequencies of the parts are never a multiple of 3, okay? So that's why you don't have 4 plus 1 plus 1 plus 1, because 1 appears a multiple of 3 times. So that's why these are the only partitions where you have frequencies that are not multiples of 3, and there are 8 such partitions. And the partitions where the frequencies are incongruent mod 3 are in the left-hand column. And how did we proceed? We took the thing that appeared most and added it to every instance of the second thing. So the thing 511, the thing that appears most is 1 1. And so we take the 5 and add it to one of the ones and we get 6 1. Here we have 2 3s and a 1. The 3s appear most, so we add a 3 to the 1, we get 4 3. Here the 2s appear most, so we add a 2 to the 3, we get 5 2. Here the 1s appear most, so we add a 1 to the 2, and we get 3 and 4 1s. And so the bijection works perfectly when n equals 7. Next slide, please. All right, here's the case where we have n as a multiple of 3. And I've listed at the top of the screen the 8 partitions where there is a preimage in P1 and shown the mapping between P1 and P2. The same construction that I just went through at n equals 7 goes completely through here for n equal 9. But there are still some P0 partitions sitting there. And really, what was the criteria? The criteria was that the largest part is twice the size of the smallest part. And as you see, here's 6 plus 3. That basically corresponds to the divisor 1. And here are the 3 partitions corresponding to the 3 as the divisor of 3, where you have the 3 different possibilities for having different 2s and 1s. And so you see that sigma 1 of 3 is 4, and here are the 4 partitions that fail to have a preimage in P1. So I hope this sort of makes clear what was happening in the proof. Next slide, please. So let's step back a little. One of the very interesting aspects of this proof is that we see congruence conditions on the frequencies of the parts rather than on the parts themselves. Those of you who are intimately involved in the theory of partition know that the Rogers-Ramanujan identities and umpteen jillion other identities of that nature, Rogers-Ramanujan parts not congruent to 0 and plus or minus 1 mod 5, or congruent to 1 and 4 mod 5, congruent to 2 and 3 mod 5. Schur's partition theorem in parts not congruent to 1 or 5 mod 6. And in Schur's theorem, you have difference between parts at least 2, but if the parts are congruent to 3, then their difference is bigger than 3. And you have conditions like that throughout. There are an extremely large number, I'm sure it's still finite, but there are extremely large number of theorems in which this congruence classes of the parts involved plays a central role in the theorems being asserted. Whereas here, the parts are almost irrelevant. I grant you that at the end, it is of concern that one part is twice the other part, but for the most part, in the bijection, especially when you're dealing with an n not divisible by 3, the part that doesn't matter with the parts, congruence for the parts are irrelevant. But the congruence nature of the frequencies is absolutely crucial to what is going on. And this is something that I have not seen there are some sort of fringe theorems on this, but there's not been any serious concentration on this. Next slide, please. It is unlikely that this is the only theorem of this nature in the theory of partitions. Next slide, please. Especially when we write partitions, often we write partitions as the linear combination you see in here. And this shows a very symmetric role played by the frequencies and by parts. So I suggest that at least one lesson that I hope people carry away from this is that a study of partitions where the frequencies and their special plays plays a more substantial role. Next slide, please. There is much more to the story. The UT of A and Q are quasi-modular forms. We prove that in this paper. I'm not going to go into that. There are other congruences as well. Next slide, please. For example, the argument that when A is 1, then for arbitrary t, the 3n plus 2 case is congruent to 0 mod 3. And m0 of 1, t, and 3 and n, m0 of 1 and t and n, you can obviously extend the ideas that I just described to you to prove this initial identity. You can now have frequencies f1, f2, f3, up to fk, and the idea will be that you have minus 1 to the f1 plus f2 plus fk will be the sign of effectively that. But basically, the same idea is involved, so that there should be a partition theoretic proof of this congruence I've written on the screen in the same spirit of the proof that I gave of the identity that you just saw. It is not true that M0, 1t, and 3n plus 1 is always congruent to 0 mod 3, but 3n plus 2, it is true. So there are, I hope that what I've raised here in this talk is an awareness of, well, both of the possibilities in terms of these functions, which are interesting analytically in the fact that they lie in the ring of quasi-modular forms, but also that they raise new partition theoretic questions in a domain of partitions that has really been, up to this point, somewhat neglected. And with that, I ask for the next slide. I will mention that Ken Ono has done something completely revolutionary. Namely, he has tied this up to the Hilbert's 10th problem. Next slide, please. He and his colleagues have shown that there are linear combinations of this, which have infinitely many positive values, which I didn't state on this slide, but needs to be stated, or otherwise it becomes a triviality. There are linear combinations that have infinitely many positive values, and the positive values are always prime. As I don't know, then Matiasevich's theorem was that there are multi-variable polynomials which have infinitely many positive values, and all their positive values are primes. And Ken and his colleagues have extended this using this particular function to the theory of partitions, obtaining a similarly prime detecting linear combination of these functions. So there are very exciting things happening here, spreading out in all directions. And with that, I think the next slide says, thank you. That's the end of my talk. Much appreciated.
Thank you very much, Professor Andrews, for a wonderful talk. Are there any questions, parameter? And you had 1 plus a q to the n plus q to the 2n put in
Yes.
there.
Yeah.
If we look at that quadratic polynomial in q to the n, then that is like similar to this cyclotomic polynomial 1 plus x squared. So if we have higher degree ones, could there be extensions of this?
So I would say that we have picked low-hanging fruit. In other words, if you choose the a so that 1 plus ax plus x squared, the roots of that are roots of unity, which is true for the square roots, the cube roots, the fourth roots, and the sixth roots of unity. All those are quadratic things, and those are the instances where that works. So if you were to move on to higher degree cyclotomic polynomials, what you have for yourself is the difficulty of denominator that is now starting to get away from you in terms of the world of Q hypergeometric functions. It's whether or not you could do something with that. I mean, anybody who achieves something with that, I shall honor profusely, because it seems to me like a very difficult road to hoe, but it certainly, given that McMahon wrote his original paper in, I think, 1923, and Simon Rose and I wrote our paper in 2013, so that basically you see in 90 years, nothing happened at all. And this absolute gem, I mean, it would be worth everybody's while to go back and read McMahon's paper, because McMahon was very smart, and there are very interesting things in it that have not been really touched upon by anyone at all. But this really has just sort of sprung into people's consciousness. I mean, my paper with Simon Rose, he had a particular application in algebraic geometry in mind, and that what we proved there worked his application, and we left it at that. I was president of the American Mathematical Society at the time, and so it was my contribution to that was written on an airplane, and so I didn't really start to think about what its implications might be. Tewodros Amda-Berhan is the one who raised the questions that have now just sprung into profusion. And so I think this is a rich potential area, but obviously I've told you basically things that I'm most familiar with, and I look forward to many others doing wonderful things with it.
Yeah. And I had one other question. Gaurav, can you put up the slides, please? Oh, maybe the next one, 48. So in this particular identity, if you put A is equal to -2, we get tautology, right? Because
yes, we're back to the original case.
okay.
If you put A equal -2, this is the exact theorem that Simon Rose and I proved in 2013.
Right. Okay. Thank you.